Hi everyone and welcome back to PrepFusion. I'm Anish and today we will start with the lecture 49 of our electrical machines subject. Okay, so this will be a new chapter that is synchronous machines. So we have learned transformers, we have learned DC machines which were operating in DC. We have learned actually internally it was AC as well, but with the help of commutators we were able to convert it into DC. We learned about induction motors. Mainly we covered induction motors. We can use it as a generator as well, but the main use case of induction machines is as a motor only. Now we will come to the last chapter, okay, that is synchronous machines. So it is quite similar to induction motor, but there is a big difference here. So today we will discuss why is it called synchronous. Why did the induction motor was called induction motor, right? It was called induction motor because the energy transfer was happening through induction, correct? And it was a motor because it is giving some mechanical power output. Now why is it called synchronous here? That kind of doubt you might have. So we will learn about that, and also we will learn about working principle of synchronous generator and motor, different types of rotor in a synchronous machine, right? There are mainly two kinds of rotor, just like induction motor had two kinds of rotor. If you remember, one was squirrel cage and another one was wound rotor, right? So here also we will have two kinds of rotor, not depending on the winding, but depending on the construction. We will see that. Also we will understand the rotating magnetic field in synchronous machine. Here also there will be a rotating magnetic field. Basic working principle will be same actually. Here also there will be a rotating magnetic field. Here also there will be a like stator rotating magnetic field, rotor rotating magnetic field, but the difference will be the stator rotating magnetic field and the rotor rotating magnetic field will always rotate in the will always be synchronous to each other. What do I mean by it? So basically, why is it called synchronous? It is called synchronous because here the rotor, just hold on, the rotor rotates with synchronous speed. I hope you remember, right? What is synchronous speed? So synchronous speed ns was equals to 120 f by d. That is what my synchronous speed was equals to. Okay, so your rotor also will rotate in the same speed. Actually, previously if you remember, in case of induction motor, your rotor used to rotate with slightly lower than synchronous speed. Okay, but as here the rotor will rotate exactly with synchronous speed, that's why it is called a synchronous motor, because the speed of the rotor will be synchronous speed. Okay, that is the first thing that you should understand. Why is it called synchronous synchronous machine, right? Now another point to note here is that what will be here also, there will be two kinds of magnetic field. One will be the stator magnetic field, another will be the rotor magnetic field. Okay, so stator magnetic field and rotor magnetic field. What is the speed of the stator magnetic field? The speed of the stator magnetic field with respect to a stationary observer will always be ns. Now can you tell me what will be the speed of the rotor magnetic field? So previously if you remember, I have the, okay, I don't have, where is the picture? Okay, I'm just looking for, okay, I don't have, so I will just draw the motor here. So basically I had this motor, right? And I had this stator part, and I have this rotor. Now previously what was happening, my rotor was actually rotating with speed nr, my stator magnetic field was actually rotating with speed ns. So there was a speed of difference between the rotor and the stator magnetic field. So your rotor magnetic field with respect to the rotor had to provide an additional speed. It used to rotate with an additional speed with what? With ns minus nr. Now this was with respect to what? Rotor, right? I'm just revising the induction motor working principle. Why this was required? Why did the rotor magnetic field needed to provide this additional speed with respect to rotor? Because of the alignment torque, because I knew the stator magnetic field and rotor magnetic field must be aligned with each other, then only torque production will happen, right? So something similar will happen. So now the speed of the rotor magnetic field also will be ns with respect to stator, remember, and 0 with respect to rotor. Previously it was ns minus nr, so we'll just mark it over here. Previously it was ns minus nr, now it is 0 with respect to rotor. Why? Because rotor itself is rotating already with speed ns, right? So I don't need to provide any additional speed for it to be synchronized with the stator magnetic field. Already the rotor is rotating with nr speed. How it will rotate with nr speed, I will explain that. Okay, don't worry about it. There is a reason behind why it rotates with a speed of ns, sorry, not nr, ns, right? I will discuss about that. So this was about the rotating magnetic field. Now another thing is there, that my synchronous machine is a doubly excited machine. Okay, your induction machine was a singly excited machine. What do you mean by doubly excited? Doubly excited means both the stator, doubly excited, right? Doubly excited means both stator and rotor are excited. So previously what used to happen, that we used to excite the stator side, right? We used to provide the three-phase supply in the stator side, and then it generates a rotating magnetic field. Due to induction, a EMF is induced in the rotor side, so that also in turn generates a rotating magnetic field. So both of those combine each other, right? So basically rotor itself inherently did not have any EMF of itself, right? The EMF used to get induced by the stator, but here we will actually provide a excitation in the rotor as well. Okay, in the rotor as well I will provide a DC excitation, not AC. I will provide a DC excitation. Why DC, I will explain. So both, due to that a magnetic field will be generated, and that magnetic field will be aligned with the stator rotating magnetic field, and then finally it will rotate. Okay, so this is the crux of synchronous machine. Okay, just in I guess in 10 minutes, 8 minutes, 8 to 10 minutes, I have explained you the basic working principle of synchronous machine. Of course we will dive more deeper into it. Okay, so like whatever I am explaining, same thing is written over here. Synchronous machine are a class of AC machines. It is a AC machines, same as induction motor. Okay, that operate at constant speed known as synchronous speed. This speed remains fixed irrespective of load variation. So previously, if you remember, my load torque graph or speed torque graph was something like this, right? This was the developed torque, electromagnetic developed torque, and this was the speed. So this was the graph basically, right? This was for a induction machine. Okay, this was for an induction machine. For your like if the speed changes, your torque will change. Okay, basically your if I change the load, if the load changes, then the speed changes basically, right? But here, right, because what will happen initially, if say let's say this was the load torque, right, TL1, then I change like this then this will be the stability point. How to find out stability point, I've already explained. Now if the load torque changes to here, if I reduce the load torque, so then the speed will increase, right? So this will be the stable point, right? But in case of synchronous motor, what will happen is that the speed is constant, so it does not matter whatever load I provide, the speed will be constant. So this is particularly useful where we need constant speed operation. Okay, so making them highly suitable for applications requiring constant speed and stable frequency. Stable frequency meaning constant speed meaning basically when I'm using it as a motor. So when I'm using it as a motor, I want constant speed, then I will use synchronous motor. When I need to generate power, right, like induction, also induction machines can also generate power with the help of induction generator, but there, right, the frequency will not be constant of the AC induced EMF. The frequency will not be constant because what does the frequency depends on? The frequency is depending on basically 120 F by P, right? So P into N divided by 120, correct? So your speed is changing, basically, right? In induction motor it is not fixed, your speed is not fixed in induction motor, but in synchronous motor your generator speed will be fixed. If your generator speed is fixed, then the frequency at which it will generate the induced EMF also will be fixed, right? So that is the advantage here, that is the advantage in synchronous machines. So that's why wherever you see in all the big power stations, right, we use alternators. Alternators are nothing but synchronous generators. Okay, why are they called alternators? That also I will explain. Okay, so why synchronous? As I explained, same reason they have given, that speed will be constant. So unlike induction, synchronous machine do not rely on slip. The rotor locks in with the stator rotating magnetic field and rotates. So basically what will happen, I will have a stator and I will provide excitation in the rotor. So both of them, the magnetic fields of both of them will lock with each other. If both of them locks with each other, then they rotate finally, right, with full speed. So that is what happens basically here. Okay, so I will explain that, don't worry, I will explain how does the excitation work, working principle, all those things I will explain. I'm just giving you a overview for now. So synchronous generator, also called as alternator. Why are they called alternator? Because they generate alternating current. Simple, right? They are able to generate AC current, that's why generate alternating current. Okay, so um, uh, we converts mechanical energy to electrical energy. So basically in synchronous generator alternators, what we do, we rotate the shaft, and due to that we are able to convert mechanical energy into electrical energy. Okay, we will see this in detail, don't worry, the working principle. I'm just giving you an overview, how does it work. So there are like it is, okay, I will just search for that. Where is it? I am not able to find it. Yeah, here is it, right? I was searching for this. Yeah, so basically what we'll do is, if you see, like this is one kind of rotor, I will explain the types of rotor basically. So here, right, we have this rotor side, and rotor side, what we do, we connect a DC supply, right? If I connect a DC supply, let's say I'm connecting a supply like this, so how does the current will flow? The current will flow somewhat like this, right? It will go like here, 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 here. Okay, current will flow like this. So what is the direction of the magnetic field? Direction of the magnetic field, if I curl my fingers along the direction of the current, it's going like this. Finger is on the left hand side, so the magnetic field will be somewhat like this, right? The magnetic field will be somewhat like this, correct? So basically magnetic field direction will be somewhat like this. So basically this will be the north pole because it is outward, and this will be the south pole because field lines are coming inwards, right? So it develops a magnetic field of itself, but remember it is stationary, right? And here also what will happen, this three phase balance supply will actually generate a rotating magnetic field, correct? Three phase balance supply will generate a rotating magnetic field. So what will happen, basically as this magnetic field is rotating, right, let's assume that this is the north side of the magnetic field. So this north side will basically, what will happen, it will attract the north pole. It will attract the north pole because north attracts north, and south will attract the south pole. So this end will be the north pole and this end will be the south pole. Whichever one end will be the north pole, other end will be the south pole, basically, right? I'm just giving you an overview. Okay, so the north pole, both of the north poles will get aligned, both of the south poles will get aligned. So if alignment happens, magnetic locking happens, then what happens, if the stator magnetic field is rotating, because due to locking, the rotor magnetic field also will try to rotate, right? So it will take the rotor away itself, because rotor magnetic field in itself is stationary with respect to the rotor, right? So if the rotor magnetic field is trying to rotate, it has to move the rotor, so there will be a bit of magnetic locking. Same like here, right? So this, right, if you see this, right, this earbud, here I have magnets. So if I just leave this, automatically it will get inserted, right? Automatically I'm just leaving it, it is not falling down due to, okay, now it is falling down, now it is falling down. But if we keep it close, right, it is not falling, basically. If I keep it close, it is not falling due to magnets, it is locking here, right? So same thing here, due to magnets, what is happening, as now this is like, you are not able to see the magnetic field. Are you able to see the magnetic field here? No, right? It is just magnets, it is just locking here, right? It is just locking. So same thing is happening over here, that this stator windings are generating rotating magnetic field, that we already know. Okay, now this is a, let's say this is just a north pole here by itself, right? But as we know that north, sorry, what I'm talking, sorry, I'm really sorry, north will get attracted by south, I'm sorry, extremely sorry. So here, right, let's assume this is the south pole of this winding and this is the north pole, right? And what will happen, as this is rotating, so how can I say whether one is south or north pole? Depending on the rotor current variation. So how can I say it? So if I assume, let's assume one thing, let's assume this to be dot, okay, like currents flowing through this stator for a particular instant. So how do I explain it to you? So one thing I can explain it to you is that, like, if I just draw the three phase, right, three phase current, so this is IA. So IA current will be somewhat like this, correct? Let's say with zero phase difference. Then IB current will be here. IB current will be phase shifted by 120 degrees, and then IC current will be there, right? So the key point is, whenever IA will be maximum, you will see the value of IB, right, will be something negative. Like, you will observe that. Okay, I don't have the three phase, like I will show you in the next few slides, don't worry about it, but just trust me on this. So if I assume this to be my like, why am I explaining it? Because if it, let's assume that dot here means that current is positive, right? So this, let's assume current is positive, and let's assume this is E coil, let's assume this is B coil, and this is C coil, right? So this will be A dash, this will be B dash, and this will be C dash. Okay, so if I shift this way 120, right? So basically if I shift this like here, right, if I see, if I observe it in the maxima, if I observe in the maxima, what will happen? Sorry, I'm making a mistake. Basically this will be shifted by 120 actually. So this is 90, right? So this current will be something negative, I guess. Yeah, your current will be negative, and your IC current also will be somewhat negative, if I remember correctly. Okay, your IC current also will be negative. So what is happening over here is that, okay, let me draw it, otherwise you will get confused. Let me draw it, okay? Otherwise I don't want you to get confused. Okay, it's better that I draw the three phase currents, you will understand it. So I hope you understood this winding namings, right? So simply A phase, B phase, and C phase, right? That's it, 120 degree phase apart. So windings are physically placed 120 degree phase apart, And if like these are the windings, right? Basically I have a winding AA dash, then I have a winding here BB dash, then I have a winding C dash. Okay, so 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 now let's understand the currents. So I will explain the currents very quickly. I will just draw the sinusoidal waveforms. You will understand what I am speaking about. So here, right? So let me draw the IA current with respect to time omega t. Let me draw the IA current. Okay. So it is yellow only. That is fine. So let me draw the sinusoidal current. Yeah. Okay. So this is the sine waveform of IA. Now what will be IB? IB will be same waveform but 120-degree phase apart, right? So if I draw the IB, IB will be phase apart by 120. It will lag by 120, right? So basically, if I draw a line over here, if I draw a line over here, so if the peak is happening here, right? So the peak of B current will happen after 120 degrees somewhere here. Somewhere here. This is 120 basically, right? If I just okay, let me just mark it in 120 only. 120 will be this, I guess. This will be the 120 degree. Okay. Now what will happen to C? Right? C also we have to draw. C, this is not exactly, yeah. C will actually lag further by 120, or I can make it lead by 120, right? That also I can do. So C, I can say it leads by 120. So basically it will be somewhat like this. Leads by 120, right? No, this, yeah, this will be correct. Yeah. So this will be the IC current. IC is red. Okay. Okay. Either you say lead by 120 or lags by 240. Okay. So I hope like I'm not explaining you the three-phase currents and all those things you already know. Basics you already know, right? Okay. So the important point to note here is that when the peak of, so this is 120 basically. Okay. So when the peak of current IA happens, right? When the peak of current IA happens, what is the value of the current in the B winding and in the C winding? Let me change it to this place. Okay. So if I observe one thing, that the peak IB current is negative, so is the IC current. Both the currents are negative actually. Negative meaning, if I assume the positive current to be flowing from E to A dash, then the negative current will be basically current flowing from B dash to C. So if I assume current flowing from A to A dash as dot, then like if I assume A to be dot, right, and B to be dot, C to be dot, basically, right? If I assume the non-dash to be the dot terminal, then here current is entering the dot and here current is leaving the dot, correct? So that's why this will be dot, and in here, right, it will be cross, because if you see in the B point current is leaving the dot, so here it will be cross. Okay, so I hope you understand why it is dot and why it is cross. So this will be cross, and for C as well same thing, this will be cross, and for the other parts it will just be opposite, because if I am saying it is entering here, it is exiting, right? So exiting means this will be cross, A dash will be cross, and your C dash will be sorry, your B dash, yeah, A dash will be cross, that's it, A dash will be cross, that's it. For the other ones, right, for B dash and C dash, it will be dot. Why it will be dot? Because here the current is leaving the dot at the B terminal, here it is entering, right? So it will be dot. So the other 2 points will be dot simply. So now if you observe one thing, if I see on the top left hand side, the current is leaving, right? It is dot, so it will be something like this, right? You just curl your fingers, right? Curl your fingers along the direction of the current, and in the bottom side, current is entering, right? In the bottom side, current is entering. Okay, you see all crosses are there. In the top side, current is leaving, right? So basically, if I curl my fingers, I see a magnetic field is getting generated along this direction, right? Magnetic field is generated along this direction. Okay, magnetic field is getting generated along this direction. So what will happen? It is also generating a magnetic field, but remember, I just observed at a point. I'm just observing at the peak, right? It is always changing. That's why we derive, right? We derive that magnetic field is rotating. So this is just at a point. So what will happen? It will generate. So here, right, it is leaving. So this will be the north pole basically, and this side will be the south pole, right? So now I hope you understand how does the stator rotating magnetic field is generating. Remember, this magnetic field lines I have drawn at an instant. So here I will say very specifically, because magnetic field itself is rotating with respect to time. Just at omega t equals to pi by 2, at this instant I am just drawing the magnetic field lines. It is always rotating, right? To explain you, that's why I have paused this instant, just like time machine, right? I have paused the time. I have paused the time. So this magnetic field lines is drawn at an instant. Okay, so magnetic field lines are drawn at an instant. So now what you can say is, that I am observing that yes, here I have south pole for the stator magnetic field, here I have north pole of the rotor magnetic field. So both of them again will couple. So couples, so they will make a couple, right? North and south. North and south will make a couple. Here also north and south will make a couple, right? And I know that north, this stator magnetic field itself is rotating. So as they have made a couple, so they will also move, just like girlfriend and boyfriend, right? If you have ever been with your friends, right, who are a couple, right, so they move together. It's not like they will move alone, right? So here I have couple, right, so they will always hold their hands and they will move together. They will not move alone. So as the stator magnetic field is also moving, so will the rotor magnetic field will try to rotate. But the problem is, rotor magnetic field is a DC magnetic field, right? So it is like a permanent magnetic field, it is stationary. So the rotor itself has to rotate to satisfy the condition, basically condition of synchronism and condition of couple. So basically, if your girlfriend says she wants to go to a movie, so you agree with that, right? You don't disagree with that. Same is happening. Stator magnetic field is saying, I want you to come with me, right? I want the rotor magnetic field to come with me. But rotor magnetic field will say that I am stationary, I am permanent magnetic field. But the stator will say, then what? So what? Okay, you just make the rotor move. So the rotor will move then. So that's how basically, like, then the couple will be formed, and then obviously both of them will keep on rotating synchronizingly. Now here, right, this story is kind of wrong. Like theoretically, this story is wrong. Why this story is wrong? Because the synchronous motor does not have any starting torque inherently. The synchronous motor does not have any starting torque inherently, right? Why? That I will explain later. Okay, let's not go to everything in the first lecture itself. I'm just giving you an overview. So like basics, I hope you have understood that how this alignment torque happens, how does the synchronous motor always rotates, and what does doubly excited machine means. Okay, that is clear, I hope, I guess. So same thing. I have just explained you the working of motor. Same will happen for generator, just the opposite, right? Why? Because here I myself will rotate the rotor, okay, which will generate a rotating magnetic field, right? And that will induce the EMF in the stator, and due to that it will supply Like it will basically supply three-phase balanced supply, right? It will give three-phase balanced AC supply. Okay, because I myself am rotating the prime mover with synchronous speed. Okay, very easy and simple to understand. So in case of synchronous generator, sorry, stator is not supplied with three-phase AC. Stator will supply. Actually, this is kind of wrong here, right? Synchronous generator, stator will supply three-phase AC. This is statement is wrong. Stator will supply three-phase AC because we are moving the rotor. Okay, and remember we are moving the rotor, but also we have to supply this DC in the rotor. This needs to be supplied because permanent magnet needs to be generated. So we have to supply that. No matter what, we have to supply that. Okay, so rotor is supplied with DC to create a magnetic field. Okay, that will always happen no matter in generator or in motor. In motor we will convert this electrical energy into mechanical energy by doing what? By this time the stator will be supplied with three-phase AC, and rotor also will be supplied with DC, and due to synchronism, due to this alignment torque, the rotor will rotate with synchronous speed. Okay, so it is used in industrial drives where constant speed is essential. Also it is same, it is doubly excited. Okay, so I hope you have understood, but remember in synchronous machine we will require a auxiliary starting method. Basically induction machine, it was inherently starting. Why it was inherently starting? It was inherently starting because what was happening is initially your, basically I have this rotor. Okay, do I have this? Can I paste this? I don't think I can paste this. No, yeah, I can paste this. Okay, so previously what I had in induction machine I'm talking about. So I did not have any excitation here, right? So basically this stator magnetic field was rotating, flux was getting cut in the rotor, and due to that, basically due to the slip and all those things, the rotor started to rotate because it has to reduce the speed difference between the stator magnetic field and the rotor magnetic field. But now the rotor does not care actually, because rotor itself has its own excitation. Rotor itself has its own excitation, north south. So what is happening? What will happen basically? I will give you a brief. So as the stator magnetic field is rotating, remember this is rotating, right? So initially this is north here and this is south, right? Let's say at time uh, instant t1, I have north here and south, or let me write this at time instant capital T by 2. Okay, for the half time period, right? Because your magnetic field is rotating, basically it is something like sinusoidal only, so it will keep on rotating. So for half time period, uh, okay, let me not, okay, let me say it like this, that at time instant T by 2, my north pole is here, south pole is here, correct? But at time T, what will happen? The it will totally rotate here, right? It will come, north pole will totally come here, right? Then my north pole will come here, south pole will come here. So initially, because it is a rotating magnetic field, it will not remain stationary. Initially my north pole, south pole was here. Initially my north pole, south pole was here. Now what will happen? Now what will happen is that they will swap places. So after instant T by 2, my this will reach south pole here, this will reach north pole here. Okay, and this will keep on happening, right? Again at 3T by 2, again I will have north pole here, south pole here. Again at 2T, I will have north pole here, south pole here. So if I see this rotor, okay, if I see this rotor, what is happening? Actually this rotor, the average torque experienced by the rotor will be 0. Why? Because the torque, right, will be somewhat sinusoidal with respect to time. The torque experienced by a specific point, let's say at this point, mechanically will be something sinusoidal, right? So for certain time period it will be positive, for certain time period it will be negative. So basically what is happening is I have this rotor, right, and this is the, let's say this is the rotating magnetic field, so it is rotating like this, right, and this rotor is stationary. So when like this north pole is here, this south pole is here, so initially, yeah, the north pole actually was coupled. So this, let's say this is the north pole, this front top side, this back camera top side, right, back camera top side is the north pole. Okay, so what is happening is that the north pole was here, and suddenly then the north pole came down, right, again the north pole came here, again the north pole came down. So actually what is happening is, when the instant at which the north pole was at the top, for a certain seconds, few seconds, this will experience, so the north pole will move, so the rotor also will try to move. But as the speed of the stator magnetic field is so fast, it will suddenly come here, and if it comes here, right, then the south pole is here, and the south pole actually repels. So let's say this is the south pole, right, and the south pole actually repels. So initially my rotor was moving here, right, but as the south pole is repelling, so it will somewhat move here. Basically what is happening, what will happen is the rotor will just oscillate like this, it will just pulsate. So for t by 2 time period, it will just experience a torque in the left hand side in the clockwise direction, and for other t by 2 time period, it will experience a rotation in the torque in the anti-clockwise direction. So it will just oscillate like this. So actually it will never rotate. Why? Because remember, your rotor is very heavy object, right, and your stator magnetic field is rotating very fast, moving very fast. Okay, so it is moving very fast. Rotor will not be able to react due to inertia. Okay, rotor will not be able to react. Once both the magnetic fields are coupled, then they will synchronize, then they will move no matter what. Once they are coupled, right, once they are coupled, they will move together. But during starting, this will not happen because the rotor magnetic field is very fast. Okay, due to inertia, this will not move. So what needs to happen, we need to initially give it some starting torque. We need to provide some starting torque basically. So you I guess if you remember, like if you have any motor or something, so generally if your motor gets stopped, right, what you do is you try to, like, you turn on the supply and you just give a push to the motor, okay, to the this prime mover. You just try to push it somewhere, and you see suddenly it start rotating. So it was the problem of starting torque. So actually we have to provide an initial starting torque to the rotor so that it gets aligned. Otherwise the average torque will always be zero. Due to inertia, this rotor will not rotate, it will just pulsate. Okay, so that is the problem with synchronous machine. So your induction machines are inherently starting. Okay, we don't need an external starting mechanism in induction machine. Okay, so induction machine does not need any external starting mechanism, but synchronous machine will require external starting mechanism. But for generators already we are rotating the machine, so we don't need any starting mechanism, we don't need any starting torque, right, we are already by ourselves only we are rotating the machine. But in case of motors, yes, for motors they will require a inherent starting method like damper windings. We'll learn this later on as we move along. Or any small motors which are by themselves inherently starting, so that will provide the initial starting torque because they are not self starting. So with this I have basically given you the whole overview of synchronous machine. Okay, so I hope you have understood like the difference between singly excited and doubly excited. So singly excited means in induction machine the stator was used to was provided with 3-phase AC supply for a motor, and the rotor supply used to happen with induced EMF via the stator, right, with the magnetic field due to induction. Okay, so here is the case over here. And synchronous machine, so in synchronous machine the stator will be supplied with 3-phase AC and the rotor will be supplied with DC supply. Okay, synchronous machine stator will be supplied with 3-phase AC and rotor will be supplied with DC supply. So that's why it is a doubly excited, because the rotor supply is supplied separately. Both the stator and rotor are excited, but in case of induction machine only the stator was externally excited, but here both are excited. Okay, so even though DC machines are also technically doubly excited, because field we excite separately with help of DC and armature we provide supply, right, This classification is more relevant to AC machines because we are talking about AC generators, AC currents and voltages. Okay, that I hope you understand. But DC also is kind of a doubly excited machine. Okay, you can understand it like this. Now, briefly, I will not discuss the construction totally here. Briefly, we'll go through the construction. Okay, so the stator houses the three-phase armature winding connected to the AC supply, okay, which produces a rotating magnetic field when excited by a three-phase source. Okay, so yeah, this we already know, and usually the stator side will have four terminals. So remember, like this is my machine, okay, and the stator always will be provided with a three-phase balance supply, and the rotor always will be provided with a DC excitation. नाउ वाई इज दैट द केस? आप बोलोगे ऐसा क्यों है भाई, तुम स्टेटर को खाली थ्री फेस बैलेंस दे रहे हो, रोटर ने क्या गलती की है? वट वट like bad things has rotor done that you are not providing the three phase? Like both is possible. Like I can provide three phase balance supply on the rotor side and I can provide DC excitation on the stator side. That also will work. But why we don't use it, right? Think about it. In the next slide, the answer is there. Okay. So rotor side will carry the field winding excited by an external DC source via slip rings. We will see like what are the different kinds of rotors, that also we'll see. Produces the rotor magnetic field which synchronizes with the stator's rotating magnetic field. So this is a summary basically synchronous about the synchronous motor. Synchronous motors, the speed will be constant, excitation will be doubly excited, starting it is not self starting, okay, induction is self starting. Okay, so here right I can also provide the basically I can provide the difference for induction machine. It will be the best. I forgot to write the induction machine. So induction machine, the speed is variable, right? Induction motor, the speed is variable, depends on load. Okay, excitation here it will be singly excited, right? And it is self starting. It is generally used as a motor, like universal motor. Whatever you see motor, right, in industrial industries, whenever you will use a motor, mostly you will use induction motor only. Why not synchronous? Because synchronous has few problems. Yes, constant speed is there, but if I increase my load torque very high, right, it will not rotate at all. Okay, but induction machine, if I increase my load torque very high, still it will rotate. Yes, the slip will be higher, yes, the rotor speed will be lower, but still at least it will rotate. Okay, so that's why mostly in industrial motors you will see induction motors are used. Okay, so here there is slip, right? Slip will be basically equals to ns minus nr divided by ns. Okay, rotor types, like here there are two types of rotor. One is salient pole and cylindrical. In case of synchronous, one was squirrel cage, another one is wound. Okay, then most common in power generation. So in generators mainly we use it, and this is most common in induction. Sorry, in industries. Okay, so this was the difference basically. Now let's understand this key question, that why the rotor side is DC excited, we are not providing three-phase supply, and why the stator side we are providing three-phase supply. Okay, think and I will come back with the solution. So let's like get to this question. Why is the armature winding placed on the stator and the field winding on the rotor in synchronous machine. Why does it happen? That why am I placing the armature winding on the stator side, armature winding placed on the stator side and the field winding is placed on the rotor side. So there are many reasons behind it. So if you see, like, these are the two configurations, like this is just a rotor, okay, rotor box. So in this box, either I can place the field winding or I can place the armature winding. Like, working principle will be same, both will work. Okay, I'm just telling you from now onwards itself that both configurations will work, right? Both configurations will work, but you have to understand which one is better. Actually, this one is better. Why this one is better? Because here, first of all, you observe that the number of slip rings required is lower, right? Because you have a rotating component here, so you will need brushes. So brushes, slip rings, all those things, right? Here it will be required lower, so less number of brushes and slip rings. Okay, less number of brushes and slip rings, so the number of slip rings and brushes required will be lower. That is one of the advantage. What is the other advantage? Other advantage is, if you remember, the armature generally carries higher current, right? If the current is higher, then the wires required will be more thicker, right? So here thin wire required, right? So basically my cost will go down. Thin wire required, so cost goes down. Okay, cost goes down. Now one more thing, remember that generally the armature voltage is higher, right? If the armature voltage is higher, then there is a possibility of breakdown happening, right, between these 2 points, because we need to have a neutral as well. So there can be a possibility of insulation breakdown here, right? There can be a possibility of insulation breakdown. Okay, so there can be a possibility of insulation breakdown here, so we have to provide proper insulation between the slip rings, either or else they will be short circuited. But here, it as the voltage already is very low, air should be sufficient, right? Air is also a insulating medium only, but if the voltage becomes very high, then we cannot insulate these two slip rings. We have to provide other insulating materials in the slip rings. But already in field windings, the voltage will be pretty low, right? If the voltage is pretty low, already I don't need to provide any additional insulation. The air is enough. So cost, again, cost reduces. So in whichever way you look, operational wise, the operating principle won't change, right? But if I use my field windings on the rotor side, then ultimately what is it? Ultimately everyone wants to save on cost. You also want to save on cost. That's why you are watching this video free on YouTube. You did not want to buy any course, right? You are watching free on YouTube, so you also wanted to maximize your cost, right, return. So they also want to maximize their cost, so we can maximize it if I place the field windings on the rotor side and not on the stator side. Okay, these are the things. So minimizing the number of slip rings, reduce insulation requirements, okay, better mechanical stability. One more thing is there, if armature windings are placed right as a rotor, so I have 3 windings to take care. So previously, if you see, if this is my rotor, so this is very lightweight, right? Very lightweight, I can easily rotate it, no problem. But if I have 3 things like this 3 windings, right, 3 things will rotate, so something can get damaged easily. The higher load you want to rotate, something can happen, right? So like armature winding, if I use it as a rotor, it does not provide better mechanical stability. Here if you see better mechanical stability at high speed, it does not provide better mechanical stability. Okay, so the armature winding is heavier and bulkier than the field winding because it handles higher currents and has tons of thicker wire. Okay, so that's how it is better. Okay, so improved cooling and heat dissipation. Okay, improved cooling and heat dissipation. Armature windings carry large currents which generate significant I square R copper losses. Okay, which build up heat. So yeah. So yeah, like those windings, all those things will be heated up, right? Because the currents are higher. If the currents are high, I square R losses will be higher, so heating will happen. So for those also I need to provide additional cooling. And whenever things are stationary, providing cooling is one thing. If it is already rotating, I have to provide extra effort. So the cooling also, the cost of the cooling also will increase, right? So to maintain efficient cooling is essential to maintain winding life. So cooling systems we have to use effectively because the winding itself are rotating, right? So that automatically increases the cost. Okay. So these are the problems basically. That's why we use the uh, field windings as the rotor, armature winding as the stator. Okay, these are the comparisons. I hope you can understand why is the reason. So basically everywhere else, everything, right, in everything the stators like the armature on the stator is preferred, right? So why we will use the other one? If it is advantageous to have the armature on the stator side, why will I use the armature on the rotor side if the working principle is same, right? So that's why in everywhere else you will see that your armature winding is always in the stator side. Now briefly let's understand the working principle of synchronous generator. Okay, so in a synchronous generator, the rotor is supplied with a DC excitation, right? As we have discussed, either via slip rings. So these are the slip rings, right? This will be the slip rings where I will provide the DC excitation. Current will flow basically to the rotor, and then the like magnetic field will be developed. And in the stator as well, I will provide like I will not provide anything. I will rotate the rotor. So what will happen? A rotating magnetic field will be developed because remember it is just like a permanent magnet, right? That rotor side is just like a permanent magnet. Now I myself am moving the handle, so it will rotate, right? It will rotate. So what will happen basically? It will develop a rotating magnetic field, and that rotating magnetic field will induce a EMF, just the opposite of motor, right? So what will be the equation of that EMF? This we have derived in the induction machine, so I will not explain over here. So this will be the equation for the induced EMF. Extra term is there, kW. Just for now you understand kW is just winding factor. Okay, kW is just the winding factor. Okay, I will explain this later at the end because not that important. I will explain this later at the end. What does this winding factor actually means? Okay, this will come. We will come to this at the end. Okay, so this is the induced EMF, right, in the stator side, and from here I will take out the supply. So actually, I will take out the supply from here. Very basic working, right? Now, as it is a constant speed generator, right, your rotor speed will be fixed. If your rotor speed is fixed, your frequency is also fixed. If the rotor speed is fixed, your frequency is also fixed. Okay. What about synchronous motor? In synchronous motor, the motor operates on the same principle but in reverse. Here, a three-phase AC supply is given on the stator, creating rotating magnetic field. The rotor, excited by DC, locks in synchronism. I've already explained this. How does it lock? And when the stator field rotates exactly at synchronous speed, that is 120 F by P, like then what happens? The rotor also rotates with the same speed. Okay, so there is no slip here. Already we have explained this. Okay, it's kind of repeated, right? Already I have explained like what are the cases over here. Okay, so the construction I will go through a bit. So construction is here. So construction of synchronous machine. So uh, I will go into the winding types later at the end, but briefly again the same thing, similar, like everything will be similar only. Here I will have a stator, I will have a rotor, right, and then I will have frame, all those things. I'm not going into those things right now. I'm just interested in the stator side and the rotor side. So stator is a stationary part that carries the armature current. So the stator is almost structurally identical to three-phase induction motor because there also we used to provide three-phase supply on the stator side only. Okay, so it is composed of a cast iron or steel outer frame which serves as a protective enclosure and mechanical support. Okay, a limited slotted stator core made of silicon steel to minimize the current losses. Okay, a laminated slotted stator core made of silicon steel, so it needs to be laminated, right? It needs to be laminated due to reduction of the eddy current losses. Three-phase armature windings are embedded in these slots and are spatially distributed by 120-degree electrical. So again same thing, right? A winding will be here, then physically this will be spatially distributed by 120 degrees. Again the C winding will be spatially distributed by 120 degrees. So if you can see the angle difference here, 120, 120, 120 between the phase A, phase B, phase C. These windings are responsible for producing or receiving the AC electrical power. It will produce the AC electrical power if it is working as a generator. It will receive the AC electrical power if it is working as a motor, because I will provide the supply then, right? So yeah, lamination is why it is done. It is explained over here. Now let's discuss about the rotor. What does a rotor do? Now remember, these windings can be both connected in delta or star. It's not like here, right? It is looking like it is star connected. It will always be star connected. No, that is not the case. We can connect it in either star or delta. We can either connect this on star or delta. Okay, does not matter. Here you're observing it is kind of star, but we can connect it in both ways. Okay, so it's not like it will always be like A, B, C like this. It can be like multi-layer winding. All those things can be there. I'm not going into it constructionally. Okay, there can be many slots. All those things will be there. Okay, so mainly the stator side is provided to properly, like here also it is written, the windings can be connected in either star or delta. Okay, and mainly the purpose of this is to carry the three-phase balanced current. That's it. That is the purpose of this, right? What about the rotor side? Now rotor, right? Rotor is responsible for carrying the DC field, right? It carries the DC field excitation. DC field excitation. Okay, which produces a constant magnetic field required for synchronous operations. There are two main rotors. There are two main rotor design based on application. Okay, so basically there are two kinds of rotor. One is a cylindrical pole rotor, another one is a salient pole. So what is the difference between cylindrical and salient pole? So in salient pole, the winding type is concentrated winding. Okay, don't worry about this. This we will discuss in later. This will discuss later. And in cylindrical, the winding will be distributed. Why it is distributed? So if we see, right, if you see, all the windings are concentrated here only on particular places, but here if you see, the windings are distributed, right? Kind of distributed. It will be distributed throughout actually. So windings are distributed here, right? But here one is dot, one is cross. It is concentrated here. Here it is concentrated. Here it is concentrated. Okay, but here it is kind of distributed. Now the next point is the air gap. If you observe, right, is constant here. If you see from here as well, it is same. From everywhere, the air gap is constant, right, throughout. So here the air gap is constant. So constant air gap. But here if you observe, here the air gap is minimum, but again here if the magnetic fields are here, the air gap is higher, right? Again here it is minimum, again it is higher somewhere here. So air gap is variable. Air gap is not constant here. So this is the basic difference between a cylindrical pole rotor and a salient pole rotor. So a salient pole rotor basically resembles just like a permanent magnet, north south, right? North south, just like it. And the windings are wound over on the poles, just like poles. It is just like poles. But here, right, windings are in slots. So here slots are present in cylindrical, here poles are present. Okay, so we will see the difference one by one. So the construction of cylindrical pole rotor, also called as non-salient pole rotor. Okay, remember this name is pretty important. And remember, if this air gap is different, right, this will provide a very important characteristics that we will learn later on. Okay, so here the construction will be uniform, smooth, cylindrical surface. Okay, construction will be uniform, smooth. Okay, and it will be a cylindrical structure. Basically the air gap will be uniform throughout. Okay, so rotor is symmetrically wound with distributed windings. Distributed windings means the windings are distributed throughout the slots. Here winding is concentrated, here winding is concentrated, here it is concentrated, right? But in case of your cylindrical rotor, winding is distributed. The air gap between the stator and rotor is always uniform in all directions, but not in case of a salient pole rotor. Okay, these rotors are robust, can vary at high speed. Now why they can vary at high speed? Okay, can work at high speeds. Why they can work at high speeds? Basically, if you understand this, right, rotating a circular object and rotating this object, right, are very different things. Okay, because this is uniform, symmetricity is here. So rotating this, right, okay, this is not a good example. Yeah, rotate this. If you see, this is circle, right, rotating this will be much easier for me than rotating this, because this will provide a moment of inertia, because this is elongated in the y-axis and the x-axis, right? There will be a bit of moment of inertia, so there can be basically inertia here. There can be inertia. Okay, but like due to that, due to mechanical problems, I cannot actually rotate this at a very fast rate. Okay, why? So that is the first problem. I cannot rotate this at a very fast rate. Okay, that is the thing. One more thing, one more thing you can understand is that here, right, making more number of poles is kind of different, right? Because we have distributed winding and I have to place the winding such a way, so making the higher number of poles is difficult. But here, right, it's very simple. I just add one more structure and I wound the windings through that, so I will make a pole. So in case of a salient pole rotor, I will have more poles here, and as this is slot dominant, so this will have less poles. So I know one formula, right? If I know one thing, that my n is equals to 120 f by p, or my f equals to p into n divided by 120. Okay, so this is what my f is equals to. Now if you understand this thing very carefully, that I told you that of course if I am generating something, right, frequency must be fixed. If frequency is fixed, and for a salient pole rotor I can have more number of poles, so the speed has to be lower, right? So in like this also you can understand why is the speed lower, but mechanically if you try to understand it, speed has to be lower in salient pole rotor only, otherwise there is higher chances of it getting damaged, right? Because if I rotate this in a high speed, right, because this is elongated, there can be mechanical problems, physical problems. Okay, not electrical, physical problems. Okay, so in cylindrical, as it is uniform, right, there is less probability of it getting like blasted or something, or some like what do you say, mechanically it getting disturbed. Okay, because it is symmetrical circular. Okay, so that is the thing over here. Yeah, so one more thing, if you see like this, right, as it is totally circular, so the torque required will be almost constant here. But here, right, that this is not a uniform structure. So if you have studied physics, you will understand, if it is not a uniform structure, so to rotate this, right, the torque has to vary. So if torque varies, right, there can be a bit of mechanical instability problems. That's why we don't operate our salient poles in high speed. Okay, I've given you multiple reasons why we don't operate salient pole rotor in high speeds. Okay, so yeah, commonly used with turbo generators. We'll understand what are turbo generators. Basically, turbo generators are those kind of generators which are used in steam turbine, gas turbine. So in your power plants, right, steam power plants or gas power plants, in those kind of power plants you will see always we will use turbo generators which are obviously synchronous generators whose pole will always be non-salient pole rotor. Why? Because if I am using steam in steam power plant, I can have very high speed, right? Very high speed. Like the winds can provide very high speed. So if the winds are able to provide very high speed, then I don't need like which kind of rotor structure supports high speed salient non-salient pole. That's why in uh, steam power plants we use non-salient pole or cylindrical rotors. Okay, I hope you have understood this thing. So advantage, due to symmetrical construction, uniform air gap, they offer low windage loss. Suitable for high speed applications. Okay, as I have mentioned, fewer poles, the number of poles will be lower. So it is used in steam power plants or thermal or nuclear generation plants also it can be used, but mostly it is used in steam power plants. So always you will see in steam power plants always we are using our non-salient pole rotors. Synchronous generators we will use in power plants, we use synchronous generator only, but there can be two types, one is salient, one is non-salient. So in steam power plants we will use non-salient pole rotor. Now one more thing is there. Okay, where is that picture actually? Yeah, I will explain that picture later. One more thing is there about the salient pole rotor. So in a salient pole rotor, what happens? The projecting poles are mounted on larger diameter rotor. So this is larger diameter, the projecting poles, and the other portions don't have any windings. They are just there for support. Okay. Each pole individually is wound and protrudes outwards. So individually as they are wound, so it is concentrated in particular positions. That's why the name concentrated winding. Concentrated. Okay. The air gap is non-uniform, smaller under the poles, larger between. So air gap is non-uniform. So it is very small under the poles but larger here, right? So air gap here is very large and here it is very small. Okay. So air gap is not particularly uniform. That is a problem. Due to mechanical limitations, as I have mentioned, the rotor operates in low to medium speed, typically below 1000 rpm. So that's why we don't use this in steam power plants, because in steam power plants the operating speed must be very high. So we generally use this in hydroelectric power stations where the speed of the river, right, steam speed is generally low, right? If speed is low, then this kind of rotors are very useful. So that's why you will see salient pole rotors getting used in hydroelectric power stations. Okay, the mass is even unevenly distributed. The mass is unevenly distributed, causing a centrifugal force imbalance at high speed. Okay, so yeah, why? What is the problem? Because here the mass is uniformly distributed, so the torque required also will be uniform, constant. But here, right, as mass is non-uniformly distributed, so there will be a centrifugal force. What is centrifugal force? So if a particle is rotating like this, right, in this direction, so it will have a centripetal force, centrifugal force. If you remember mv square, I also don't remember actually, mv square by r or something. I've also forgotten, right? So this formula was there, mv square by r or something. One was centripetal, one was centrifugal. I don't remember, but something like this is happening over here. So yeah, due to that, right, due to this unevenness, basically, what will happen? This cannot operate in high speeds. Okay. Yeah. So hence high speed operation is not suitable. Used in application where the prime mover is hydraulic turbines, hydroelectric or diesel engines. Okay. So typically designed with more poles. So hence like frequency must be constant. So frequency is proportional to speed into number of poles. If speed is lower, then the poles must go up high, because I want to produce at 50 hertz only, right? Because our supply, all those things operate in 50 hertz only. So that's why we will basically increase the number of poles. So in salient pole, in salient pole rotors, the number of poles will be higher than the non-salient pole rotors. That is the cylindrical pole rotors. Okay. So yeah, simple construction, easy to maintenance, high torque at low speed due to multiple poles. So if multiple poles are there, torque will be higher at low speeds. Okay. Okay. So as I am explaining, so there are two kinds of alternators. One is hydro alternator, in which the rotor will be salient pole. So these two alternators are used in generating power, right? Mainly these are the two machines that we use for generating power. Okay. So hydro alternators are used in hydroelectric power plants. Hence, we will use salient pole rotors here. Okay. Number of poles will be generally higher here. Okay. So if the number of poles is higher, right, the rotor diameter must be larger. Okay. Because what you are observing is I have to accommodate more poles. This pole also I have to accommodate, this pole also I have to accommodate, this pole also I have to accommodate more poles. If I am increasing the number of poles, this should provide me enough diameter so that I can insert enough number of poles over here. So that's why you will see that the diameter of a salient pole rotor will be higher. Diameter will be much greater than the length for a salient pole rotor. Okay, so this is the structure of the rotor basically. Of course, individual poles are there, right? Individual poles are there. I'm not drawing the poles. I am not drawing the individual poles. I'm just overall drawing the cylindrical structure. Of course, it is not cylindrical, right? My rotor will be, of course, not cylindrical. I will do one thing, otherwise you will get confused. So what can I do? What can I do? This, right? Can kind of connect these things. Like roughly I'm drawing, these are the poles basically. There will be more poles, but the diameter will be higher here. Okay, so just drawing it for the sake of it, just to explain you, diameter will be higher than the length basically, dimension wise the comparison, right? So yeah, here in case of turbo alternators, like you can go through this points you can go through, I'm not explaining everything. Okay, in case of turbo alternators, what will happen, as it is like high speed, I cannot keep on increasing the time. So the more diameter I increase, basically what will happen, there can be this centripetal force, right? The centripetal force will be more lower, right? Basically there is a force that attracts it towards the center. So if R increases, right, this is lower, the centripetal force is lower, so there is more probability of it falling back. So what do I mean by it? So basically, right, this is rotating, right? Now this is some small thing, so it will not flow away, right? But let's say if this was this large or more larger, right, if I rotate it at very high speed, there is a possibility that the two parts, right, two parts can flow away. Or I can show you, like basically you can see the fan, right? Okay, can I show you the fan? Okay, there is the fan, right? So those are the wings of the fan. So these are the wings of the fan, right? So now if the wings, basically I am just changing my camera. So if the wings are very large, if these wings are very large, what will happen? Basically they will blast away. If the wings are very large and if I rotate the fan at very high speed, the wings will simply separate from the body. Okay, so why is it happening? Because this R is very high. If this R is very high, then the force that was attracting this wings to the center has reduced. So the attraction force has reduced and there is a force that will try to take it out, right? It is, why is it stationary? If you see, it is not going away, right? So there are two forces, one is centripetal, centrifugal. I'm not explaining everything over here, but the attraction is equal to the repulsion, I mean basically the force that is giving it outward. So as they are equal, that's why it is still in place. But if I keep on increasing the R and if I increase the speed, right, so centrifugal force, the force that tries to take it outside, depends on speed. Okay, the more higher the speed, the more probability of it going outward from the center, right? And this v, it also depends on this v, right? It also depends on this v, correct? So if the speed is higher, so there will be a outward force, okay? So v also will increase, okay? At a certain stage, what will happen if this r is very high, okay? So the internal force that is pulling the wing inside will be lower, so basically it can go out. So the main point is, I don't want to go in physics right now. The crux is basically, if I increase the diameter, there is a probability of these wings getting like separated from the body, right? These wings can get separated, right? Separated. So that's why we don't use this hydroelectric in high speed, but turbo alternators must be used in high speed only. As we have explained, we have to use it in high speed because the number of poles are low. So if we have to use in high speed, hence here the length will be larger than the diameter will be much smaller for mechanical stability, okay? So they are used in thermal gas power plants. So it has smooth surface and it has long axial length and small diameter, making it more compact and balanced for high speed rotation, okay? So these are the important points. And one more thing, it is horizontally mounted for stability. Horizontally meaning mounted like this only. It is mounted like this, okay? And your hydroelectric is vertically mounted, okay? Vertically mounted, basically it is mounted somewhat like this, okay? It is not mounted like this, it is mounted, I'll just rotate this, mounted like this. Okay, I cannot reduce the size, that is a bummer. Okay. Can I reduce the size? Yes, I can. Okay, so it is mounted like this, okay? It is vertically mounted. It is written over here as well, better suited for vertically mounted. So in hydroelectric stations, you will observe that it is vertically mounted, right? Because due to mechanical stability, okay? And it is mounted horizontally, same due to mechanical stability, okay? So yeah, I hope you have understood this difference between turbo alternator and your hydro alternator. So this is, you will learn in power systems as well why we use this. Now I hope you understand why we use non-salient pole in turbo alternators and salient pole in hydroelectric plants, okay? So trust me, no one will do this, like they will try to insert power systems here and explain intuitively what is the reasoning behind each of this, right? So they will directly go into the topic, but I'm trying to give you a link, a holistic picture of all the core subjects here, okay? So the summary already is written, you can go through this. The summary already I have explained this, I don't need to read this over again, okay? So yeah, synchronous generators are widely used in power stations. So in everywhere else you will see synchronous generator getting used to generate electrical energy due to their ability to provide constant frequency, as I have already explained. Synchronous motor will be used where constant speed is required even if there is load variation, okay? So yeah, the important points, the output frequency is directly related with the rotor speed and the number of poles. Synchronous machines can also run as synchronous condensers, okay? I will explain what is condensers later, okay? With, it depends on excitation basically. So we will learn this today. I will give you a crux basically, what is excitation I will give you. So in this first lecture only, like we will get an idea of what is to come, right? Everything we will get an idea, okay? In modern power systems, large synchronous generators are the backbone of energy supply, especially because their voltage regulation and their reactive power control. So we can control the reactive power as well, okay? And in everywhere else, in India, everywhere else you will see synchronous generator are used to generate electricity, okay? Alternators basically. So I hope you have understood this basic point. And now let's come to the important point of the working principle basically, okay? This I already have explained. So whenever you have, before like understanding how synchronous machines work, there are few fundamental principles, right, which will work irrespective of which machine you are. It's either it's DC machine, induction machine or synchronous machine. It should always be present. In DC machine as well, if you remember, there was a field winding and there was an armature winding. Both were actually developing the magnetic field, but due to commutator it was changing the direction of the magnetic field, basically not the direction of the magnetic field, it was changing the direction of the induced EMF. So in the output of the DC machine you were always getting a DC supply. Okay, but these two things will always be there, that the rotor poles and the stator poles must be equal to each other, otherwise there cannot be torque production. Why? Because there needs to be alignment torque, right? The north pole of the rotor and the south pole of the stator must make a couple, right? So basically, if a system is at balance, like you are going out with your friends, right? So you have, let's say, two friends, right? One is a boy, let's say Ram, another one is a girl, let's say Shushmita, right? So Ram has his girlfriend, okay? So he made a couple, and Shushmita also has his boyfriend. So you are the person who is not balanced. So of course you will say, I am not going out with you guys, okay? I'm not going out with you guys. You will say, I will go alone, okay? So same thing, something similar is happening over here, that for a system to work properly, the number of poles in the stator side and the rotor side should be same always. So as let's say I have two poles, right? So N1 S1 will align, N1 of the stator and S1 of the rotor will align with each other, and N2 of the stator and S2 of the rotor will align with each other, and the other poles as well. Basically the S1 of the stator, sorry, N1 of the rotor, so S1 of the rotor, S1 of the stator and the N1 of the rotor will be aligned with each other, and same S2 of the stator and N2 of the rotor will be again aligned with each other. Okay, that's it basically. So yeah, that's why the number of poles must be equal, otherwise how the alignment torque will work? How the hell alignment torque will work? So they must be equal to each other, so for proper synchronization. And the relative motion between the stator magnetic field and the rotor magnetic field must be zero. The relative motion between the stator magnetic field and rotor magnetic field must be equals to zero. Okay. So in synchronous machine, although the stator field rotates at synchronous speed, the rotor must also rotate at the same speed to make the relative speed zero. That's why the rotor in synchronous machine rotates with speed ns. So in case of synchronous machine, nr equals to ns. All this I have already explained. All these have been already explained to you. So same thing, right? Same, I am not explaining it over again. This already has been explained in induction machine. So same, if I provide a three-phase balanced supply in stator side, it will develop a rotating magnetic field, which will in turn produce alignment torque with the rotor side. So which, due to which the rotor also will rotate, given that you are applying a starting torque initially. Okay, so all this I have already explained in today's lecture also. Okay, so I'm not going through this over again. So this is the equation for the rotating magnetic field. Okay, so the few key points you should understand, already have explained this, right? So the speed of the rotating magnetic field with respect to the stator is ns. The speed of the rotor with respect to the stator is ns again. The speed of the rotating magnetic field with respect to the rotor will be zero. Previously in induction machine, if you remember, it was coming out to be speed of the rotating magnetic field with respect to rotor. If you remember, because it had to rotate a bit faster than the rotor to make the relative speed zero, it was ns minus nr to complete this difference. Okay, so yeah, I hope you have understood. This is why synchronous machine are called synchronous, because the rotor is locked magnetically to the rotating magnetic field. So like already I have explained, why is it called synchronous? This is why it is called synchronous, because the rotating magnetic field gets locked with the stator rotating magnetic field. So both of them align with each other. Okay, so yeah, I hope you have understood. But in case of generator, what happens? So this was for a motor, right? In case of generator, so in case of generator, what we do? We rotate this, right? this is developing a DC field, but I am rotating the rotor, due to which a rotating magnetic field is there, due to which a voltage gets induced in the stator windings. And I know just vice versa, if I have a rotating magnetic field that is cutting the stator coils, it will develop a three-phase balance winding. Just the opposite. Just the opposite. Okay, same thing is written over here. Whatever I have explained. Okay, I don't need to explain again. So this is the summary basically. So there is no concept of slip, and these are the speeds. You must remember this. You must remember, not remember, understand this conceptually. Okay, because I know GATE has not yet asked a question from this basic things, right? But one day they will ask you, and trust me, no one will be able to solve it because they don't study it with basics. They just study formulas. Okay, but I will teach you everything with basics. So now I will go through a brief about armature reaction, right? Also, don't worry if you don't understand now itself, because we will dive more deeper into it. But before going into synchronous machines, like numericals and all those things, I just wanted to give you a bit of overview about armature reaction. So let's discuss about armature reaction. So I will just give you an overview that we have this rotor, let's say rotating, and I know what is the magnetic MMF produced, right? We have already discussed about that. It's a rotating magnetic field. So this is the magnetic MMF, right? So okay, here it is written alpha. Maybe I should change it to alpha only, because theta is used for power factor angle. You will get confused, right? So what I will do, I will change this to alpha. Otherwise, you will get confused. Okay, so this is alpha basically, and this is the like MMF, rotating MMF, right? So my MMF and flux are proportional, right? Because in a cylindrical structure, the MMF, like what is my flux? Formula for flux, right, is equals to MMF upon reluctance. So what is, like, it is FF, right? MMF produced by the field winding. It is equals to, let's write this some phi m pp, basically the peak MMF per pole into cos of omega t minus alpha. Okay, now interesting thing to note here, let's assume that I am somewhere, the alpha equal to 0 is this, right? This is the axis for which my alpha is equals to 0, right? And let's say I'm rotating in the anti-clockwise direction, meaning my rotor is rotating in the anti-clockwise direction. So if let's say I am at this point, right, with respect to this conductor, let's assume this conductor is A and this is A dash. Okay, just an assumption. Currently nothing is connected. Okay, it is open circuited, nothing is connected. Now if this is a rotating magnetic field, if I observe with respect to this conductor, what is the EMF induced, that I want to know. So one thing I told you, that for a salient pole rotor the reactance will be different, right? For now let's assume that reactance or the reluctance will be different, because in this the reluctance is different, here the reluctance is different. But let us just for a second assume that the reluctance is constant. Okay, for a cylindrical pole rotor we know reluctance is constant. Let's assume that it's a cylindrical pole rotor only. Just to explain you this, I have put it like a salient pole, because here the north and south pole are easily represented. Okay, so I am at this point. So what is the flux that this point A will observe, right? This point A is stationary here. So what is the value of alpha here? So I have had to rotate in the clockwise direction by an angle of 90, right? So clockwise meaning it will be negative angle, so it will be minus of 90. So alpha will be equals to minus of 90 degrees. Alpha will be equals to minus of 90 degrees, because I have rotated in the clockwise direction. Okay, so my FF will be, or I can write basically, as my flux is proportional to mmf only, I can write my phi, right? Flux will be equals to phi peak per pole, what is the, whatever is the per pole flux, because maybe I will have multiple poles, right? This is one, due to the one of the poles, maybe I will have multiple poles. Due to only this pole I am calculating. Okay, this will be cos omega t minus of minus 90. So this will be phi mpp omega t plus 90 degree. Okay, now what is the, this is for the conductor A. What is the induced EMF here? So we know the formula for induced EMF is E is equals to minus n d phi by dt, right? Whatever is the number of turns, I don't know how many turns it is wounded, so it will be minus n into d phi of A over dt, because whatever is the flux that is linking with the conductor A. Okay, so this will be equals to, now differentiation is of, this is what, this is simply minus of sign, this is simply minus of sign, right? So like, I hope you remember, right? This is my cos theta, okay, and my sin theta is here, correct? This is what my sin theta is, but I'm adding 90, so I'm somewhere here, right? I'm adding 90. So this already I've explained in my network theory class, so I'm not explaining it over again. How am I remembering this, right? Cos 90 plus theta. So this is sin omega t, so this will be minus sin of omega t. I will not explain, okay? Already I have explained in network theory. So this will be what? This will be minus n into phi m is just a constant into d phi of dt into minus of sine omega t. So this ultimately will come out here, right? The value will come out to be induced EMF of the coil A, right? Induced EMF of the coil A will come out to be n phi mpp. Already we know this actually. It will be cos into omega, obviously will be there as a constant, into cos into, yeah, cos of omega t. So what do we observe in terms of phasor? So if I say that if the flux is here, right, this is the direction of the flux, okay, because you see that the flux is projecting here, right? This is the direction of the flux is coming outward like this, north and south pole, for a particular instant I'm talking about. So for a particular instant, if the flux is in this axis, right, along the negative x axis, then what about the induced EMF? So the induced EMF due to the flux, right, will lead by 90. So sorry, not lead, sorry, lag by 90. So this was plus 90, the flux was plus 90. So this lags by 90 degree, right? Lagging means I will go in the clockwise direction. Okay. So my induced EMF due to the flux in the stator coils will lag the field winding flux by 90 degrees. Okay, this is the most important part. Okay, that is the main summary that I wanted to give you. Okay, so all this is not that important, already we have discussed, so I think I don't need to explain this. So this is already been discussed, right? Yeah, so this is what happens in no load condition, when the armature is not connected to any load. Basically we are not supplying anything, when the current IA is 0. Now what will happen? Can you just guess what will happen if IA is not equal to 0? If IA is not equal to 0, there will be an induced EMF in the stator. And if IA is not equal to 0, basically it is supplying a load, delivering a load. So this current will be non-zero. If this current is non-zero, due to current, a flux will be generated. Whenever there is current, there has to be a flux, because the stator coils itself will generate a mmf. Now all of it depends whether what is the power factor of the load. So here, right, I will have a generator. So let's assume this is the generator, right? This is the generator, stator windings. I'm just drawing the per phase equivalent. Now what will happen, I will have a load connected over here. Now depending on the power factor of the load, right, it will decide this is the current, armature current, and this is the induced emf ef. So this load, right, load power factor will decide the angle difference between the current and the voltage, right? So if, like, and one more thing, we know that the flux is directly proportional to mmf, and I know that mmf is directly proportional to current because it is n into I. So whenever there is current, there will be mmf. If there is mmf, there will be flux. Okay, and that flux will interact with the field flux, correct? And that will overall change the resultant air gap mmf in the air gap, basically. Okay, because the mmf was only ff due to the field windings, but due to armature it will also generate a flux that will change the resultant mmf in the air gap. Okay, that is what is known as armature reaction. That is what we have learned in dc machines as well. Okay, so in no load, when the armature operates in no load, no current flows. The only flux present in the field winding, which is purely sinusoidal, is a rotating magnetic field. Hence, no armature reaction occurs. So basically, the resultant EMF is this only, and resultant flux is this only. Okay. Now, what happens in unity power factor? In unity power factor, this will be there. Field flux, MMF, induced EMF will be there. Now, due to this induced EMF, if it is unity power factor, I am delivering a unity power factor load. What does that mean? That means the phase difference between the EMF and the current will be 0 degrees. So the IA also will lie in the same phase as the armature current. Just give me a second. Okay. So IA is lying in the same phase. So will be my MMF. Okay. So will be my MMF, that is here. That will be FA. Now, of course, what will be the resultant MMF? Again, the resultant MMF will be the vector sum whenever there are two vector quantities, because it depends on the what do you say? Depends on the direction. So we will just add the two MMF. So here I will have FF. So this will be the resultant MMF, basically FR. And this will be actually not that high. This will be low only, not that high. But here I'm just showing you a bigger value. But in reality, this will be not that high value. So what is the effect of MMF here? Okay. And one more thing I forgot to tell you, that this was the induced EMF in the coil A. What will be the induced EMF in the coil B? The induced EMF in the coil B will just be 120-degree phase apart. Okay. So as it is balanced, so this will be induced EMF in the coil A dash. Coil B dash will just be N 5 mpp omega cos of omega t minus 120 degrees ECC cos omega t plus. So one more thing, that if you remember, right? So if in case of a motor, like what will happen? Not a motor, sorry. Basically, I am providing it a torque. Okay, this is the torque that I am providing. So let's say it is a generator, right? So I am providing a prime motor torque that is in this direction, or I am rotating in the anti-clockwise direction. So I am providing the generator a torque in this direction, T prime mover, right? Now, if you remember this thing, that the generator itself will develop a torque, right? Machine itself develops a torque that is known as Te. If you remember it, correct? It will be opposite. Why? Because I am rotating the generator and giving it a torque, and the generator is rotating at a constant speed. So omega is constant. How is it constant? How can the speed of the motor be constant or generator be constant if I'm giving it a torque? It should always accelerate, because generator itself is giving a backward torque, Te, right? So I hope now it is clear that how is omega constant. This we have already discussed, that whenever speed is constant, that means the forces are balanced. Okay, in this case, if you see, what is the value of this developed torque? So the value of this Te is proportional. This we have derived in DC machines as well. If you remember, it was proportional to the field mmf into the armature mmf into the sine of the angle between these two mmfs, right? This is the delta. Okay, sine of the angle of these two mmfs. In this case, delta is 90 degrees. So basically, that basically means that the armature reaction is cross magnetizing. It basically means armature reaction is cross magnetizing. Okay, why is it cross magnetizing? Because the overall field flux, I'm not changing the value of the overall field flux, I'm just changing the direction of the resultant field. Okay, that is what. Okay, we will see when it is not cross magnetizing, you will understand this even better. Okay, so just changing direction of resultant field flux. So same thing is written over here with when the alternator supplies a unity power factor load, the armature current is in phase with the terminal voltage. Basically, if I draw the circuit, I will have a armature induced EMF, I will have a armature resistance, like I will have a leakage reactance of the windings, right? Also I will have another, so this is right leakage reactance XL. Also I will have a JXAR. Now this value will keep on changing, we will see this. Okay, now remember, one more thing you have to remember, that this is my load current, right? So whenever I say power factor, I actually just say the power factor with respect to this point IA and this point, right? So it is actually known as the internal power factor. Why internal power factor? Because what you have to understand is, if I'm saying the power factor of the load, then if this is unity power factor, right? If this is unity power factor, there will be some VT voltage, there will be some IA current. So this will have zero phase difference. That is correct. But due to this reactance component, there will be phase difference between EA and IA, right? Because these are imaginary components, right? So that's why we are not discussing about the power factor in the load actually per se. We're discussing about the power factor before the connecting the load here at this stage. Okay, that is the best position, because I am not taking into account all these things. Okay, don't worry, today I'm just giving you an overview. In next lectures we will understand this more deeply. Okay, I'm just giving you a summary of what is to come. Okay, so we are only discussing about the power factor here with respect to EA and IA. This is also known as the internal power factor. Okay, so the internal power factor, if it is unity, then our armature reaction will be cross magnetizing. Okay, so yeah, I hope you have understood this thing. So resultant flux remains relatively stable because I am not reducing the overall mmf, but the it gets bit distorted because the direction gets changed. That's it. Okay, now let's discuss about lagging power factor. What will happen in lagging power factor? In case of a lagging power factor, we know that the armature current will lag the armature voltage. Again, it is internal power factor, so it will be somewhere around, like, it is not dependent on the load, it is dependent on here, right? So basically the armature current will lag, basically it will be 90 degrees in the clockwise direction to EA. So it will lag, so this will be IE. What will be the flux? So the flux, right? Flux will be here. Phi A. So the flux is here. This is the armature current. And what do I observe? I observe that it is a demagnetizing effect. Why? Because if you see the resultant flux, right, it will be phi F minus phi A, because phi F is here, phi is here, so it is actually opposing it, right? It is opposing the main field flux. Okay, so it reduces the net magnetic field. And is there any torque generation here? There will be no torque generation. Electromagnetic torque will be zero, so we cannot have purely inductive loads, right, or capacitive loads. Because one more way you can understand is, how is the electromagnetic torque here zero? Because it is what, ff into fa into sine of delta, angle between them. So sine 180 is simply zero, right? What actually takes, like, what can actually produce torque? Torque is what? Torque is real power, right? Real power. What kind of load consumes real power? Resistance, resistive load, right? So if there is resistive load, there will be torque developed. But if there is inductive load, there will not be any torque developed, because my inductive load does not consume any power, active power, right? So that's why the developed torque will be zero. So this is another intuitive way to understand how is the developed torque in the generator zero. Okay, trust me, no one will teach you in this whole industry like whatever I'm teaching you with intuition. Okay, now same thing for leading power factor, it will be magnetizing. How it will be magnetizing? So if I copy this, right, in case of leading, the current will lead the voltage, so basically the current will be here, right? This will be my armature current for a leading load, and the flux will be here, phi A. Okay, so overall if you see resultant flux, this time resultant flux will be what? This will be phi A plus phi F, both are in the same direction. So that's why it is known as, it causes a magnetizing effect, as the armature field aids the magnetic main field flux. Okay, so but again, will there be any torque produced? Again the torque produced will be zero. Why? Again, there is no real load connected, right? A resistive load. So again, sine of d 0, because the angle between the fluxes is 0. So sine of 0 will be 0 only. So developed torque will be 0. Okay. So yeah, I hope you have understood this basic point. What about for a motor? For a motor, right? How you remember this? So I'm just giving you overview, because this is the most important thing that you need to remember in armature reaction, right? So you remember the generator, and for motor, effect of armature reaction. Write this in. Okay. armature reaction will just be opposite to that of generator. Okay, so this thing you have to remember, and I will explain also with reasoning as well when you study the topic. I have not explained the topic yet, we have not done, I'm just in the first lecture, right? So I'm just giving you an overview, that's it. Okay, so in case of motor, what will happen in case of motor? If the load is lagging, the effect will be magnetizing. If it is leading, the effect will be demagnetizing, just the opposite. Okay, don't worry, I will explain this all when you will study about the this topic basically. So one more thing you have to understand is here, right, we have assumed the reluctance to be constant, but for a salient pole the reluctance will be not be constant, because here it has high reluctance, air gap is more, here I have low reluctance, right? So all those things we will take into effect when we will actually study the topic. For today I think that's it basically. So yeah, I will not explain this here, that will come later on. So for today I guess that's it. So like the relative angle delta between the field flux and the armature flux is crucial for determining the load torque developed. As load increases, the delta also will increase, right? Basically delta value generally lies between 0 to it lies between, so delta is here, right? So the load field, if it is leading current, somewhat it will be leading, yeah. It can lie between, delta can lie between 0 to 180, right? So basically if the load increases, what will happen? The delta angle will increase, because I know sine delta, right? uh, like basically what is the developed torque? Developed torque is proportional to sine delta. Okay, and what will be the, I'm just trying to understand what will be the maximum angle. Is it 180 really? Yeah, maximum angle can be 180 and minimum can be 0. Okay, so basically between 0 to 90, right? If my delta is between 0 to 90, 0 to 90, then if I increase delta, this sine delta value will increase, hence the torque also will increase. Okay, after 90 what is happening? Because the sine graph is somewhat like this, right? Between 0 to 90 it is an increasing function, after that it is a decreasing function, so it can decrease as well. This statement is not always true. Okay, so all of, like, it depends on load. If I connect the load, if I connect a load there, whatever load I'm connecting, the delta angle will vary both for motor and generator, right? In case of generator, what is the load? Armature current, right? Current. So if I change the current, this delta angle also will change. Okay, if the load demands some different amount of current, this delta angle will change. For a motor, what is the load? It's simply a mechanical load, right? So if I change the load there, if I connect a heavy load, this delta angle will change, because delta angle needs to increase, because the developed torque needs to increase. Don't worry, we will understand this dynamic behavior. Okay, now this statement is only valid when the delta angle is between 0 to 90. Okay, the spatial position of the magnetic field determines the whether the net flux is increased, decreased, or just distorted. Okay, so it depends what kind of like how the magnetic field is spatially distributed depending on the load. If it is here, overall field flux will increase. If it is a leading load, if it is here, the overall field flux will reduce, demagnetizing. If it is a unity power factor load, it will be cross magnetizing. Okay, the phase difference between the voltage and current determines the nature, that is demagnetizing, cross, or magnetizing of armature reaction. Graphically, we have already represented everything. So in synchronous generator, voltage regulation is directly influenced by the armature reaction. Okay, we will see this how it is influenced, because depending on the type of load, the induced EMF can change, and if the induced EMF changes, and depend on the current drop, right? So basically the voltage drop across the armature resistance and the leakage reactance will change. So output the terminal voltage can vary. Okay, so all this we'll learn. So today I'm just giving you a overview. So under heavy inductive loads, excessive demagnetizing can lead to voltage drop unless compensated, because overall the flux is reduced, right? Under capacitive load, over voltage can occur. Why over voltage can occur? Overall the field flux is increasing. The more the field flux, the more the induced EMF. Okay, lesser the field flux, the lesser the induced EMF. Okay, so I hope you have understood this basic point. So that's it basically. So in this lecture only I give you a overview. I'm just speaking it again. Okay, so from the next lecture onwards, actually we will study like the equivalent circuit of salient pole rotor. We will not study the construction right now. We will study the construction at the end. That is not important. Okay, we'll directly go into the equivalent circuit, because basic working principle already you know. So today we will learn about the working principle of synchronous motor, because in induction motors we had already covered that, right? So we were just revising few things, and few new things were there that I explained. So from next lecture onwards, we will go into the numerical analysis of synchronous machines. Thank you, and I will see you in the next lecture. Until then, happy learning.